Alright, welcome to the after work video. So this video is the second part of chapter 15 of this wonderful book I've been reading for all the right reasons. So this is big data tools and components, big data tools, components, and platforms. And previously we read about small data. Another way to discuss big data is to break it down into tools and platforms. Figure 15-1 shows a typical big data architecture lifecycle. So we've got a number of boxes here. We've got orchestration here, which fills the full thing from left to right. And then underneath that, we've got the sources, the storage, the file systems, and then we've got real-time message ingestion. And then separately, so these are all separate areas. The orchestration is a long rectangle that's separate from the data sources. And then the next one is the batch processing, unified processing, and stream processing that goes into the analytical data store. And then that's part of the analytics reporting, machine learning /AI. And that's the big data architecture. So let's discuss a few key components. Data sources. Some of the familiar sources of big data include social networks and digital transactions. As people have migrated more of their conversations and their business transactions online, it has led to an explosion of data. Additionally, mobile technology such as tablets, phones, and laptops that record audio and video exponentially create sources of data. Other data sources include the Internet of Things, IoT, which includes sensors, lightweight chips, and devices. All of this leads to an unstoppable proliferation of data that needs to be stored somewhere. The tools involved in data sources could range from IoT client/server systems, such as AWS IoT Greengrass, to object storage systems, such as Amazon S3 or Google Cloud Storage. File systems. File systems have played a huge role in computing. Their implementation, though, is continuously evolving. In dealing with big data, one issue is having enough disk I/O input-output to handle distributed operations. One modern tool that deals with this is the Hadoop Distributed File System, HDFS. It works by clustering many servers together, allowing aggregated CPU, disk I/O, and storage. In practice, this makes HDFS a fundamental technology for dealing with big data. It can migrate large volumes of data or file systems for distributed computing jobs. It is also the backbone of Spark, which can do stream and batch-based machine learning. Other types of file systems include object storage file systems, such as Amazon S3 file system and Google Cloud Platform Storage. They allow for huge files to be stored in a distributed and highly available manner, or more precisely, 99 point, and then we've got 9 nines. So that's 11 nines reliability. There are Python APIs and command line tools available that communicate with these file systems, enabling easy automation. These cloud APIs are covered in more detail in chapter 10. So I like to think about this 11 nines here in terms of how long is it down over the course of the year. So let's have a conversation with ChatGPT about that, because that makes this a much more understandable number. Okay, so given the number of above, that is the availability of a service throughout the year. What is the percentage of time a service is available throughout the year tell me for how long during the year will the service be unavailable.
To find out how long the service will be unavailable during the year, we first need to calculate the percentage of time it will be down. This is given by 100% minus 99.9999999%, 100% 99.9999999%, 100% minus 99.9999999%, which is 0.000000001%, 0.000000001%, 0.0.
Yeah, so here's the answer. 0.0003 seconds. You won't have access to this service if it is up for 11 nines. So let's do it for how about for ba and ba. Okay, so if we have one of those nines missing, so now we have 10 nines instead of 11. It goes from 0.003. Yeah, so it just moves the decimal. So of course it does. So yeah, every 9 you can add to that is going to make a big difference. In fact, to the point where you have these 5 nines, that's about 5 minutes and 26 seconds down during the year, which can be significant if you have a advertisement or some sort of like 5-minute video. That can be enough time to where you know that whole video is lost at some point during the year. But if it's just down for 0.003 or even 0.0003, it's just a blip, and everyone can still see the service that was meant to happen at that time, even if there is an outage. All right, so yeah, so there are Python APIs and command line tools available that communicate with these file systems, enabling easy automation. These cloud APIs are covered in more detail in Chapter 10. Finally, another type of file system to be aware of is a traditional network file system, or NFS, made available as a managed cloud service. An excellent example of this is Amazon Elastic File System, Amazon EFS. For a DevOps professional, a highly available and elastic NFS file system can be an incredibly versatile tool, especially coupled with containers technology. Figure 15-2, so containers technology, I don't think, hopefully I don't have to, Docker, Kubernetes, whatever else. That's a brand name that offers container technology as its service. Figure 15-2 shows an example of mounting EFS in a container. So Container Management Service, EKS / ECS from AWS. We got our containers feeding into the network file system, NFS or EFS. Libraries data, mounting EFS in a container. One powerful automation workflow is to programmatically create Docker containers through a build system such as AWS Code Pipeline or Google Cloud Build. These containers then get registered in the Cloud Container Registry, for example, Amazon ECR. Next, a container management system such as Kubernetes spawns containers that mount the NFS, Network File System, right? Isn't that what this stands for? Yeah, Network File System. This allows both the power of immutable container images that spawn quickly and access to centralized source code libraries and data. This type of workflow could be ideal for an organization looking to optimize machine learning operations. Cloud data storage. Ultimately, the data needs to live somewhere, and this creates some exciting opportunities and challenges. One emerging trend is to utilize the concept of a data lake. Why do you care about a data lake? A data lake allows for data processing in the same location as storage. As a result, many data lakes need to have an infinite storage and provide infinite computing. For example, be on the cloud. Amazon S3 is often a common choice for a data lake. The data lake constructed in this manner can also be utilized by a machine learning pipeline that may depend on the training data living in the lake, as well as the trained models. The trained models could then always be A/B tested to ensure the latest model is improving the production, prediction, interference system. So I don't know what the prediction system is, or also known as the interference system. A/B testing is just when you show your user base, you show half of your user base one version, and then you show the other half the other version, and whichever version you show does better, you after a short period of time to determine who the true winner is. So just for, I don't know how it's actually conducted, but let's say like for a week. So let's say like you have a YouTube video, and you want to know which thumbnail is going to get the most users. So you post the video twice, one with thumbnail A and one with thumbnail B, and then the video that gets the most views is the video that has the better thumbnail. So now you update that other post so that they both have the same thumbnail. And you don't post it twice. There's probably built-in A/B testing tools out there. But basically the idea is you show your audience different things, and then eventually you learn what things your audience responds to the best, and then you only show them those things. All right, so streaming data. So here's the data lake. It's a low-cost, secure and scalable way to store data. You can stream data in and out of it. You can use external big data tools like Spark and Hadoop. You can do machine learning with it in and out, and then you can use it for archival. Other forms of storage will be very familiar to traditional software developers. These storage systems include relational databases, key/value databases, search engines like Elasticsearch, and graph databases. In a big data architecture, each type of storage system may play a more specific role. In a small-scale system, a relational database may be a jack of all trades, but in a big data architecture, there is less room for tolerance of a mismatch of the storage system. An excellent example of a mismatch in storage choice is using a relational database, such as a search engine, by enabling full-text search capabilities instead of using a specialized solution like Elasticsearch. Elasticsearch is designed to create a scalable search solution, while a relational database is designed to provide referential integrity and transactions. The CTO of Amazon, Werner Vogel, makes this point very well by stating that a one-size database doesn't fit anyone. This problem is illustrated in figure 15-4, which shows each type of database has a specific purpose. All right, so this is kind of my rule is if I see a name, I want to follow them on LinkedIn. So I'm going to try that with Werner Vogel. I'm not sure if he's still the CTO of Amazon. Probably a good follow, though, so I think I will follow him on LinkedIn. So I'm looking at figure 15.4. It says that it's Amazon databases, and it's a children's drawing, of course, because this is such a simple, straightforward concept. No, so it's titled Purpose-Built Databases. We've got the types of databases. So we've got relational, key value, document, graph, in-memory, and search databases. And then we have the purposes. So for relational database, you would want it for transactions. For key value, you would need that for low latency key value queries. For document databases, you use them for indexing and storing documents. Graph databases are used for creating and navigating relationships. In-memory databases are used for microsecond latency. If all you care about is how fast you can read-write to the database, you need to use an in-memory database. And then the last one, search databases, are used for indexing and searching semi-structured logs. So let me read that quote again. One size database doesn't fit anyone. So you can't just use one of these databases and be fine. You have to use either multiple databases, one for each of the purposes you have in your application or your organization. So if you want to have low latency key value queries, you need to use a key value database. An in-memory low latency database won't cut it, because even though it has microsecond latency, it's not for key value queries. So you have to use that key value one as well. You can't just use your in-memory and say, oh, well, now I need key value. I have a purpose for key value queries. Well, good thing I have a in-memory database. The latency is so small, it should be fine. Well, no. I'll read the quote again. One size database doesn't fit anyone, so you have to stand up another database for the that is built for the particular purpose. All right, so now I will go to LinkedIn, and I will search for the CTO of Amazon, or I'll search for Werner Vogel, who may or may not be the CTO of Amazon. So it looks like there's quite a bit of Werner Vogels out there in the world. I believe I am pronouncing that right. Okay, so I don't see let's see who the current CTO of Amazon is. Oh, you know what? There's an S, so that's why he wasn't coming up. Okay, so yeah, here he is. He is now the VP as well. He's still the CTO of Amazon, but it looks like he got a promotion since this book was written. And let's see when he actually got that promotion, if it's on there. So, oh no, it looks like that was always his title for the last 19 years. It's not a new development. So yeah, I might as well follow. I don't know. Sometimes I worry that I follow too many people, but it's okay. This is kind of something I do without thinking about it. It's yeah, and it's just following that's different from connecting. So hopefully it makes sense. I can see some of his activities, so stuff like this is going to be showing up in my feed now. Which okay, should be fine. Sometimes I'm a little bit protective of my feed though, because I don't want to get like sniped into wasting my time on LinkedIn, or like being upset by like the things I see or anything like that, or just see stuff that's like not relevant to me and have all the relevant stuff get flooded out. But anyways, picking the correct storage solutions, including which combination of databases to use, is a crucial skill for any type of data architect to ensure that a system works at optimal efficiency. In thinking through the design of a system that is fully automated and efficient, maintenance should be a consideration. If a particular technology choice is being abused, such as using a relational database for a highly available messaging queue, then maintenance costs could explode, which in turn creates more automation work. So another component is to consider how much automation work it takes to maintain a solution. Okay, so I'll advance my bookmark and I'll delete the old one. All right, and then I've got this random old bookmark here that I'll delete as well. Okay, and now I want to have a short discussion with ChatGPT about this. And I want to get rid of this there, okay? So what I would like to talk about with you, ChatGPT, is something I just read in a book. So what I read is that there exist purpose-built databases, and it's very important to use the correct database for the correct purpose. So some examples of databases are relational, key value, document, graph, in-memory, and search databases. And some examples of purposes are making transactions, executing low latency key value pair queries, indexing and storing documents, creating and navigating relationships, optimizing for microsecond latency, and finally indexing and searching semi-structured logs. So one thing that is really important to avoid is technology choice abuse. Technology choice abuse would be something like picking one general sort of database and thinking that you only need that for any purpose. So for example, if you choose an in-memory database because all you care about is low latency, but then you want to do key value pair queries, you want to do indexing and storing documents, you want to do transactions, now you're using a database outside of the purpose for which it was intended, and as such, you're increasing your maintenance costs and you're increasing the amount of work required to maintain your product. So what I am asking you to do is to help me know the unknowns and to give me basically some sort of like mind map or some sort of graph or like some sort of tool that I can use so that if I have a purpose and I need a database, that I know very clearly which database I need to use for my purpose so that I can avoid this trap of technology choice abuse and I can make the best possible decisions to have my databases fit perfectly to my purposes for needing a database so that my maintenance costs are minimized and my ability to automate is maximized.
Creating a mind map or decision tree for selecting the right type of database based on your specific needs is a great approach to avoid technology choice abuse. To help you make informed decisions, an online guide that categorizes various types of databases and matches them to appropriate use cases. This will help you determine the best database type for specific requirements. Types of databases and their ideal use cases. Relational databases. Purpose: best for structured data with complex queries and strong consistency needs. Use cases: transactions, complex joins, and data integrity enforcement. Examples: PostgreSQL, MySQL, Oracle. Key value stores. Purpose: high performance for simple query patterns. Retrieve value by key. Use cases: session stores, caching, real-time data fetching. Examples: Redis, DynamoDB, etcd. Document stores. Purpose: flexible schema for semi-structured data. Use.
Yes, create a very detailed version of the mind map. So one thing I would also like to be included in it is an example real world scenario that would use this. So the output you had before was pretty good. It had the purpose, it had the use case, and it had the examples. I really liked the examples of those particular databases. For example, Redis database, a SAP HANA database, Elasticsearch. But where I thought things were missing was in the purpose. I understand that this is probably the best way to state what the purpose is for a really technically minded, expert level person. But I guess what I was looking more for was like a manager or like someone who doesn't really know all the technical details, but they have some general sense of like what they need to do. So I would like that included for each, as well as like a fourth item that is attached, please.
To create a detailed mind map that includes the purpose, use case, example databases, and a real-world scenario for each database type, tailored for a managerial perspective with less technical detail, we'll use clear, simple explanations. Here's the structured breakdown I'll use for the mind map. Database type, purpose, explanation in simple terms.
Yeah, this is
Use
great.
cases, general application areas. Examples, specific database technologies. Real-world scenario, an illustrative example to show practical use. I'll proceed with generating this detailed mind map for you. Mind map details relational databases purpose, store and manage structured data with clear rules and relationships. Use cases, financial records, inventory management, any system requiring accurate record keeping with complex queries. Examples, PostgreSQL, MySQL, Oracle. Real-world scenario, managing a company's payroll system where each employee's data is linked to departments, benefits, and payroll records. Key value stores purpose, quickly retrieve data using a simple identifier, key. Use cases, storing user session information, quick data retrieval for web app.
Okay, so it's creating an image out of this, but I think this itself is perfect. They included a use cases, a new one here, and a real-world scenario. So financial records, user session information, so a shopping website storing user
The detailed
keep
mind map
track,
for database selection has been generated.
storing their carts, online news. Perfect. I really like this. And now we've got a mind map created as well. Now this is where it might get a little bit tricky. I don't know if this is going to be real. And we can see they've got some it's not accurate. The spelling is incorrect, and it looks like the connections between each are not thoughtfully created either. So unfortunately, I think the mind map is not going to be good, but I will include this in the description of the video because I think this is gold right here. This is pure gold. So I'll copy it and then open a notepad and open a new tab in Notepad and paste that in. And now this is going in the in the description. The doobly-doo is the real official name. All right, so I'm just cleaning it up here. It's not that long, so it should be not take that much time to clean up. Okay, perfect. So next thing to do is to keep on reading. At some point I'll need to stop reading, but I feel like I can definitely go longer, at least until the case study. All right, so next section is real-time streaming ingestion. You know what? Actually, I'm going to do this because this is like kind of pure gold to include and it's going to be useful. I don't want to bury this insight just in a long video with a bunch of other things. So if I create another video, I'm going to do it after this one. So I'll stop this one and I'll upload the video and I'll include that pretty insightful discussion, the result from discussion with ChatGPT, so that it's all there and it's kind of easy to see in one video. And then if I want to make another one today, I'll make it in a separate video. So that's it for this video. Thanks for watching and stay tuned for real-time streaming ingestion.